Did you hear about the statistician who took the Dale Carnegie Secrets of Success course? He improved his confidence level from 95% to 99%. And we are actually going to start interpreting confidence intervals. This will be your first time really working with them, and use them to determine point estimates, the margin of error, and the plausibility of a claim. So, using sampling to make generalizations. When we take a sample or a survey, we're trying to predict the parameter. And that would be of the population with a certain characteristic. Now, we use a statistic to estimate it, and we call that estimate, we use a statistic to estimate the parameter, and if we don't know the parameter p, in this case for proportions, we use what's called p hat. That is the proportion that we got in our sample. So this is what we call our point estimate. Now, if we got a value of 53% of our samples red, does that mean that 53% of our population is red? Well, no, because there is randomness. So we may or may not have gotten a truly representative sample. And there's sampling error in our measurement. And that's just part of life. Don't think it's horrible to have sampling error. That is part of statistics. When we make a prediction using our sample, we realize a true value or parameter could be lower or higher. And that, again, is due to sampling error. The goal of the confidence interval is to account for the size of the sampling error. So we're going to teach you how big the sampling error is based on a certain confidence level. Okay, let's go ahead and assume that we have a proportion, that the real value of a proportion is 0.6. All right, and I'm going to stick with the sample size of 100 because that's nice. And I draw a sample. Well, you'll notice, first of all, on your graph, it starts at 0.44 to 0.76. Now, in theory, all the possible values are anywhere from 0 to 1, but it's narrowed this down to the probable values, and I'll tell you why in a little bit. So if I keep drawing samples, you can see a shape beginning. Let's say I draw 1,000 samples, and you start to see this shape. What do you see? Pretty much you're going to start to see the normal distribution that I was discussing on the previous slide. So how far could our point estimate be from the true value? In theory, it could be anywhere from 0 to 1,000. So 0 to 1,000 is possible for p hat, but not all these values are plausible. Plausible means believable. You can tell that our software actually knew, because it knew the parameter, that the plausible values for our sample started around 0.44 and went to 0.76. All right. Since we are using a normal distribution, we can use the empirical rule. About 99.7% of point estimates will be within 3 standard deviations, and 95% of samples will fall within 2 standard deviations of the mean. If we want to be 100% confident, we could just say our observed proportion will be anywhere from 0 to 1. There you go. But that's not helpful. So if we lower the confidence level a little, we can be more precise in our prediction. A confidence level of 95% is super popular. I've seen 90%, 95%, 99%. Those are typically the ones we see. So what is a confidence interval again? It's the range of plausible values for the parameter based on the point estimate, all right? So the point estimate is the midpoint, which would be right there. So if we had possible values for our parameter, and this was our sampling distribution, our point estimate would be right there. And then the margin of error is the distance from the point estimate to the edge of our interval. So that's what it is. You can also calculate it by dividing the width of the interval by 2, because there's a margin of error on the left side and a margin of error on the right side. Since we expect C%, depending on our confidence level, of the samples to fall within the margin of error, we can use this to make a prediction about having captured the parameter. Note, we do not say that it is a probability that our parameter is in our interval, because once we set our interval, we've thrown our net. So it's either in there or it's not. It's just when we do throw our net in this way, how often do we capture the parameter? All right. And here's your boilerplate. You can copy this down pretty much exactly. We are C% confident. So if we did 95% confidence, we would say 95. If we said 99, 99. That the interval from the low value to the high value, so your point estimate plus or minus your margin of error, captures whatever thing you're trying to capture in context. If you do not say that, for example, we're going to look at vaping. If you leave out the vaping part, you are missing part of the response. So this is what I was talking about. The Monitoring the Future surveys nationally representative samples of 12th, 10th, and 8th grade students annually. So I went ahead and I looked this data up online. In 2019, they surveyed 42,531 students. They have response rates of 80% for students in 12th grade, with most non-responses due to student absence. Well, okay, so most of the kids answer the question. When estimating the proportion of 12th graders who vape daily in 2019, they obtained a 95% confidence interval of 0.098 to 0.140. Now, I'll be honest, their intervals are actually calculated with even more complex values. We're just going to pretend it's a simple confidence interval. So how do we interpret it? Well, the interpretation is actually the same. We are 95% confident that the interval of 0.098 to 0.140 captures the proportion of 12th graders who vape daily. So what's the point estimate? Well, that's going to be, and so here's your interval right here, the low value and the high value. What's the point estimate? It should be in the middle. So let's go ahead and find the midpoint. So our point estimate is 11.9% of 12th graders vape daily. What's the margin of error? Well, it's the distance between these two and also between those two. So I just can subtract any two of them, and I get 0.021, or 2.1% is their margin of error. I could also rewrite the interval. You might see it written this way sometimes, 0.119 plus or minus 0.021, all right? Or 11.9% plus or minus 2.1%. So that's another way to express a confidence interval. So how do we interpret a C% confidence level? Remember, so notice this doesn't say interval anymore. It says level. So it's really about what percent confidence you're picking. Remember, interpreting the confidence level is about the process of constructing the interval. It's not about what you actually got. Okay, so we're going to go ahead and explore this applet. This GeoGebra applet shows a lot of confidence intervals that are created given a certain p-value, or I should say proportion, sample size, and the set confidence level. What it's trying to illustrate is that, first of all, if we have a confidence level of 75%, about 75% of the time, these green intervals are the ones that capture the parameter. Now, when we say something captures a parameter, it's not like this parameter is moving around. For example, let's say I go to a higher confidence level, all right? What I'm doing is I'm casting a bigger net. So it's kind of like you were trying to throw a net on a target, right? Like a little fake bullhead or something, or a lasso on a bullhead. If you have a bigger lasso, it's easier to catch the bullhead, right? Once you throw the lasso, once you create the confidence interval, it's not like suddenly you're not sure if you caught the bullhead or not, okay? So if you either did catch it or you didn't. The difference when we're doing sampling is, since we don't know the parameter, it's just that we don't know if we captured it. So once you've created a confidence interval, you say, oh, my interval's from here to here. You see that one's green. It did capture it. We won't personally know if we captured it, but we're 95% confident. If we use this method many times, 95% of the time, we will capture the interval, all right? The way we say it is a C%, whatever your confidence level is, represents the approximate percent of intervals that capture the parameter when constructing many intervals. So there's a boilerplate when asked to interpret a confidence level, not a confidence interval. Here's what you can write. If you use 95% confidence intervals often, about 95% of your intervals will capture the true parameter value. Concluding when a parameter is not likely. So we can actually use these intervals to determine if something is plausible or not. So if you're given a possible value for a parameter, you can determine if it's plausible if it lies within your interval. If the possible value is outside of the confidence interval, then it is considered sufficient evidence that the value is not plausible. It's still possible, just not plausible, not likely. All right. The confidence level does not represent the probability of knowing the sample proportion for us. It does not represent the probability of the parameter taking on a certain value. Parameters aren't changing on you. It is what it is, all right? Don't claim that other samples will match yours. Also, the confidence level is the probability of capturing the parameter, not the statistic. Sometimes people say, oh, okay, my sample had a point estimate of 0.119, so I'm 95% confident that I will capture the 0.119. No, you actually did capture it. That was your sample. The margin of error only accounts for sampling variability. It doesn't include any biases that we might have. And if one of the conditions is violated, your results are suspect. Unless you're specifically told to construct the interval, then you should not. Now, I'm going to tell you when you're taking the AP test and they're saying, oh, check conditions and construct an interval. That counts. Go ahead and do it. All right. When estimating the proportion of the 12th graders who vaped daily in 2019, they obtained a 95% confidence interval of 0.098 and 0.140. So now we're revisiting the same survey, and we're going to interpret the level. It's only the 95%. I don't even have to know what the survey is about. If you use a 95% confidence interval often, about 95% of your intervals will capture the true parameter rate value. Can we use this interval to claim that more than 10% of 12th graders vape daily, and why or why not? Well, 10% is 0.100, right? So it actually falls inside of the interval, right? And even if you say, well, it says more than, close enough. But in theory, 0.099 is in our interval, and that's not more than 10%. So we can see a counterexample. What that means is we do not have sufficient evidence that more than 10% of 12th graders vape daily. What type of bias could there be in the survey, and how do we expect it to affect our estimate of the parameter? Well, you guys have told me frequently that you believe the surveys underestimate the proportion of 12th graders who vape. Why? You say, well, they'll just lie. In other words, that's called response bias. They don't want to admit to vaping. And that means, what does that mean in terms of our intervals? So you should be able to take the bias and say, is our statistic going to overestimate or underestimate? In this case, we believe it will underestimate the parameter. Now, a confidence level of C% can also be seen as specifying the percent of samples that are predicted to lie in the middle of the sampling distribution. So that works. The critical value Z star fences off the expected lowest and highest values that would contain whatever percent of the samples. This formula is actually on your math chart, and it's a statistic is plus or minus your critical value, and we'll go over that more next lesson, times the standard error for the statistic. Now you're probably going, wait a second. We learned standard deviation. What's a standard error thing? It's really going to come more into play when we look at means, not so much proportions, but standard error is because we're getting the well, it does a little bit in proportions. Standard error means you're getting the standard deviation from a sample instead of from the whole population. So standard error is kind of like that S of X, whereas standard deviation is really sigma of X. Sometimes you don't want your plus or minus to be that large. So how can we make the confidence interval tighter? Well, we could use a smaller critical value, but that means our confidence level will lower and we'll be less confident. We could lower the standard error. So remember, we're getting this value from our sample, and it's proportional to 1 over square root of the sample size. This means we can lower the standard deviation by increasing the sample size. So we're going to revisit our survey one more time and presume you could cut the margin of error in half. So what would the new confidence interval be? Well, my old margin of error was 0.021. So my new lowers, I'm just going to subtract from my point estimate. There's no reason to think it'll be any different than the point estimate for the center. And I'll just subtract half as much and also add half as much. So if I kept somehow the 95% confidence level, I would say we are 95% confident that the interval 0.1085 to 0.1295 captures the proportion of 12th graders who vape daily. So how could we cut the margin of error? We could be less confident, all right? And I haven't taught you how, you probably could figure out how to calculate what the new Z value will be. We can do that more in the future. We could increase our sample size. If we quadruple it, then the standard deviation would be cut in half because 1 over square root of 4 is 1/2. And so it's cut in 2 because 2 is the square root of 4.